into GitHub. Glad to have you here today. Talk about algorithmic lattice surgery and the work you've been doing. So yeah, go ahead, take it away. I think let us know if you want us to interrupt questions or wait to the end. But yeah, whatever format you prefer. We'll take your
Yes, it's
thoughts.
totally fine if you just put the questions in. Make a sound or something. I was hoping it was on Discord the last time on Discord. You know, I love the quack. It's so funny. It's like quack. But anyway, I assume must have some sound for it. I shared a full screen in case I need to change windows, but can you see the slides?
Yeah, looks
Okay,
great.
excellent. So, um, TopologicIc is part of the TQAC ecosystem. The first thing that I will do is to show you the full view of the ecosystem, although we'll focus on topologic on the um, talk. So in general, what TQAC is aiming for is for a fault-tolerant compilation processor, a compiler. Um, it is able to take circuits designed in a wide variety of frameworks. Uh, I like Qiskit, but we have tested it with Pitkit, we have tested it with Crisp Jasp, and we are very close to like get one with Circ. We have tested it at work, but we don't have it public yet. From there, you can like upload it into PySix. Most of these tools will support to CASM, and you can put that into PySix. Some of the tools can export directly into PySix. After that, you use topologic to make a 3D version of that circuit, and we'll talk about what a 3D version entails. And after that, you can bring it into TQEC, make it a circuit, and simulate with that circuits. Eventually, you'll also be able to like run it on actual computers. So now let's focus on this red bordered area. We're going to start a little bit by what's lattice surgery, which is what topologic does. It does algorithmic lattice surgery, but we're going to do it in a very different way as done usually. We're just going to focus on the outcome of a lattice surgery. And the outcome is something that's called a space-time diagram. That's for all practical purposes a 3D structure that represents a lattice surgery. Now, the lattice surgery, in case there are like proper physicists in here, so that they're not like too disappointed at me. The lattice surgery is a method for merging and splitting surface code patches. And the surface code is a method itself for interweaving qubits in a way that makes error correction possible. Now, the specifics of this, if you want to like talk about them, I definitely recommend you to hit the TQC group. But the point here is more like there are different levels of representations in everything. And if you go from like the very micro all the way to the macro, a macro level of representation for lattice surgery is this 3D structure that you see there. And what you do with it is essentially a little bit like what you would do if you were making the air conditioning ducts of a building. You need the air to get from one side to the other one. So as long as the structure is topologically correct, which is the technical term, as long as the structure doesn't bend in weird ways or breaks or like the continuity of the structure fails, the air will get from one side to the other one. So for the practical matters and the way that I first understood this challenge is a 3D optimization. I just need to make a structure that doesn't break. And for that, we have rules. So in that sense, shapes are material. It means because the surface code is planar and because you need to run it many times, you are building a structure that has 2D in physical space and then 1D in time. And those dimensions are real. I mean, you cannot forget about them, and they make an actual physical structure that you can plot in a 3D graph in the same way that you would plot an air conditioning duct. And the colors are sort of material. The colors are tied to the underlying colors of the surface code, and those colors of the surface code are tied to the ways in which you interweave the qubits. So they tell you, they communicate information that is available in the surface code. And the way that you ensure that the uh, structure doesn't break is essentially by maintaining the color continuity. And that's that. I mean, if you want to see it from a programmer's perspective, that is lattice surgery. As long as you get the outcome you need, how you build it, it's important for the theory, but it's not as important for the practice. Uh, Also important is that you don't need to go patch by patch. You don't need to like start with one patch and then do another one and then do another one because, I mean, there are many, many patches in there. They are blocks of, we can think about them as prefabricated pieces of the air conditioning duct or prefabricated pieces of the lattice surgery that you can use to deliver certain operations. So for example, here on the screen, you see the blocks needed to do X set um, edges, including hot hammer edges. And while the Y one, we haven't implemented it yet, but that's also the block that you have. These blocks have been tested in TQEC. Yeah, we know that you can build a structure using these representations. They're called primitives, and you can turn it into a circuit that can be simulated. So they predated topologic. What topologic does is make graphical or spatial use of the blocks. And remember, the colors are still the key. If you match the colors of the adjacent blocks and do that for every single block in the sequence, you get a 3D structure that doesn't break in terms of topology. You get a continuity of color, which again, it represents the continuity of the internal mathematical operations that happen. Um, I'm gonna go from like general to specific. So first, let's look at a general run of topologic. What it does is it takes a ZX graph you have there in the little corner, and the ZX graph you can build it like with a wide variety of tools. If you know how to design a circuit, you probably know how to send a circuit to ZX graph. If not, then just look for the documentation. There'll be like an export to CASM, and the CASM you can like load it into bisex. Then on the first little corner here, you see that it makes one choice. The first block is selected randomly from high centrality nodes, and then it selects a random kind. The kind, I didn't explain that well. If you see these blocks, they have names. That is the kind. So you refer to each of these blocks by a different name, and the kind matches the colors and matches the direction in which the colors are oriented. So what you do is to select one randomly from high centrality spiders, place it, and then start edge by edge. You put this one. And once you put that one, you have this edge. So you go to the next one and you do it. As long as you maintain the color continuity, you'll be fine. And at the end, you'll get a big lattice. If you go edge by edge, you are really only placing one cube, which are the square ones, and one pipe in most operations. So it really is just a matter of being systematic in how you build a 3D structure. At the end, you're going to have some edges in the graph that you didn't consider in single cube, single pipe moves. But there's also a kind of operation that allows you to make long paths. It's a shortest path operation where you can just connect any remaining edges by defining one as a start and the other one as a target, and then it builds you the path. So that's what it does in general. And the rest of the presentation, what I'll do is just to like go into the specifics about the different parts of like this process. Here are more examples, which are animated GIFs. So if you put attention to only one of them, you'll see how the process goes about. Also, let's focus here on the C note. It's about to finish and it will start again. You'll see how the process matches the input CX graph. It should start in like a couple seconds, maybe. There. It goes edge by edge. Placing block, placing block, placing block. Something I want to highlight is it looks boring because it is represented at a very practical level. But I think that is, I'm very proud of it. I mean, the fact that you can make this look simple is something I really like of topologic. I mean, when I started working with this, the challenge seemed very complicated. So I think we have simplified it a lot. The performance that we have randomized test pendings. At the moment, we're testing with a panel of examples. All circuits that we have complete. However, I noted that the first initial choice is random between high centrality, which means the circuit can start at a different position, and by extension, it will like follow different paths. If you take all the paths across all the circuits, then we still have a few failures that we're looking how to solve. And the volumes are actually really good. So for example, you can do a CNOT in 2 blocks. You can do 3 CNOTs in, it goes from 6 spiders in the original graph to 12. As steen, it goes from 8 spiders to 14 cubes. And then you can do a 16 qubit GH set from 7 to 7. And that's the one you see here. It's pretty cool because the initial graph for a GH set is it really only has one node. So topologic takes that graph and breaks it into a minimum number of cubes possible, because if you see, each cube can only have 4 exits, and that is a constraint that we'll talk about later. So it cannot do all the edges at once, so you need to break it into the minimum number of spiders that you could do with 4 edges, and then it builds it just like that without any additional cube. It really does the most optimal result that you could have. Inside the algorithm is it's a dual stage BFS, so it's 2 breadth first searches put together. There is a graph manager, and that's the one that picks, well, it checks the validity of the incoming sex graph, and then it picks the first node, and it goes again edge by edge, one edge, the other edge, the other edge. Once it fulfills that first spider, it goes to one of the neighbors and it starts exploring the edges. And that's called the primary pass, like the exploration of edge by edge from the spiders of the graph. When you do that, you're going to leave some edges undone. And then the graph manager also handles the second pass, which is where it identifies any edges that we're missing and it connects them. That's I call it the outer BFS, because it manages the full process. And then there's an internal BFS, which is the one that renders the paths. So when you have an entirely new node, the the source will be already placed. It was placed in an operation before, so you cannot move it, but you can select where you go with the target. So what it does is it defines a number of possible positions or tentative positions where the next node might go, and then it creates paths to all of them. Um, and once it has all the paths to like the different tentative positions, then it sends it back to a graph manager. If the 2 cubes were defined in a previous operation, then it goes into shortest path mode, which is a spatial BFS path search, like what you have in video games, for example. When you are playing a video game and they shoot at you, the game calculates where like the path that gets to you shortest.
Excuse me.
This, yeah,
Sorry, I have a quick question.
yeah.
Um, I I'm a little confused about how we use this, and what it looks like for like the workflow of like and what this does to an error correcting code, and like going into it and then coming out of it, what the total change is. If you could just like give a brief explanation.
Could you rephrase the question a little bit?
So we start with an error correcting code, no?
Uh-huh.
And
Well,
we
we
put
saw,
it
yeah,
in, and then this like reduces it or it makes it smaller, or
I see. Okay. Let's go back a little bit to this part. So the error correction code that we're using is the surface code. So let me just start with that. Do you know how the surface code works?
Yeah.
Okay. The surface code has, depending on like the operation that you are fulfilling, it has a special pattern where you have blue edges on one side and red edges on the other side. So when you run that a few times, it kind of like creates a little bit of a continuity of the internal correlation surface. Other representations of the surface code have like a logical operator here and a logical operator here. So when you do that many times, the logical operator becomes a surface. So it's like one line, one line, one line, and the surface goes through, right? So what you do with this is ensuring that that surface remains unbroken throughout. When you get here, there are rules to know what the surface would do. Those rules, you probably have heard of them as Pauli webs. So when a surface comes here, depending on the color, it can go straight, or it can go up, or it can go in all directions. So what this structure represents is the kind of like the air conditioning ducts through which that correlation surface goes. And what it does is to preserve the continuity of the correlation surface inside. Now, the reason I don't think about that is because that is guaranteed by these primitives. So these primitives are themselves a series of a few surface code patches that do exactly that for specific operations. So if you put this primitive on a 3D space, you are guaranteeing that the succession of surface code patches delivers the operation that the primitive corresponds to. So as long, um, you see, these ones are set, right? There's three of them, correct? These are blue nodes. So you can think of each of these as one of the blue nodes in this graph. So when you build this is a 2D circuit and it's not fault tolerant in itself. To be able to run it, you need to run it in a computer, in a quantum computer, through the surface code. So that means you're going to have to change that blue circle in there for one of these cubes in here. And when you do that, the problem that you have is that if you go to the next one and you just don't think about how you are assembling all of them in the, let's call it imaginary 3D space made by the 2D dimensions of the surface code and then the time dimension, you cannot just put them all on top of each other. You need to like go left and go right, and you need to ensure that those things don't end up crashing in the end, because if they crash in the end, then you lose the continuity of the internal correlation surface. So by exchanging each of these into their corresponding cube, you guarantee that the operation itself happens. So what the rest of the algorithm does is to make sure that you can get from one operation to the other one without doing a weird bend that would break the correlation surface. Does that make sense?
Yes. Thank you.
Perfect. I was here. I think I just finished this.
We may have one other question, at least in the
Yeah.
chat.
Yeah, sorry.
Alexander.
Hi, thanks. Thanks, Jay. Like, I was curious, like, since you mentioned like pi zx on one of the slides, like, so is the procedure that kind of like you first simplify using pi zx to get like a simplified zx representation of your circuit, and then like from there build up your lattice surgery 3D kind of like circuit, or what?
Yes, yes, exactly. That's exactly it. So tell you what, I had just finished this section, the graph manager. Let me just finish this slide and then I'll go to an example that will answer that question exactly.
Okay, great.
So
Thanks.
I was noting that when you need to join two cubes that are already placed, you just find the shortest path. And then you send all the operations, all the results back to the graph manager, and the graph manager will decide which path is the best if you have many paths, or will just check the paths for integrity. We'll talk about different operations to check integrity later. Right. So before getting into key subroutines, I think it will be helpful if we run one example to, how do I take this zoom thing out of the way?
We don't see the zoom thing on our side at least, but maybe that's impossible for you, but we just see your VS Code, so it works good.
Uh-oh. Okay, wait. Okay, we should be doing. Right, so now you see my VS Code, right?
Yeah, we do.
Okay. So let's just start with this example of the GS set. And I'll just run it here. It will stop with a couple visualizations. Let's look at the terminal first. The first thing it does with this function here on top is, look, this entire script, the whole thing will get handled in less than 100 lines. The first thing it does is it just designs your foundational circuit using Qiskit. I mean, this is how you code GS16 in Qiskit. Just put 16 qubits, starts from 0, and then you just join them to with CNOTs, like cascade of CNOTs. From there, you take this Qiskit circuit, and with Qiskit's own methods, internal methods of Qiskit, you turn it into a QASM string. Once you have the QASM string, PySix has a method that is already designed into PySix, which allows you to take a QASM string and converts it into PySix, which is what you see here. Now, the initial PySix circuit, well, this is a graph that comes from a circuit, will not be optimized. And there are a couple issues with the function to bring QASM into PySix that make it impossible to make initializations and post-selection. So you do have to apply a couple manual tricks that you can see here. So this one, you apply the state, and in this circuit we don't do post-select, but you could also apply post-select here by changing one of these to 0. But in this circuit we don't need it. So once you apply states, this circuit, which is the original one that came from the QASM string, will become an optimized version of that. And here's the optimized version that PySix gives. Again, here I have done nothing. In all this process, there is absolutely nothing that I coded for this. I am just using either Qiskit methods or PySix methods with that little trick, the one line that I showed you. And this is the final reduced version of the PySix graph that PySix gives you. These cannot be built into a space-type diagram that is based on the surface code, because in 3D the structure can only have 4 edges per operation, or per node, per gate. So once topologic takes it, and here we do go into topologic, the next operation is an operation by topologic. It breaks it into more nodes. So each of these nodes, or each of these new spiders, which I know that the graph is not as pretty as PySix, but it sends them message. Each of the nodes has 4 edges: 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So once we have a PySix graph that is convertible into a 3D space-like diagram, it runs. And here we're going at it in full debug mode. The first block was selected randomly, and then it says, well, I can go here, I can go here, I can go here, I can go here. And it chooses one of those. In here, I already went in that direction, so I still have here, here, and here to go. It will choose the next one, and it basically does that for every single new cube that needs to place.
Sorry, can I ask on
Yeah.
that part? Like, so so kind of like so topologic is kind of like able to like handle to translate from a simplified ZX representation into like a lattice surgery kind of like layout?
Yes.
Okay.
Yes, that is its main and only purpose, in fact.
With minimal kind of like I don't know, minimal junctions or I don't know,
Minimal volume. Yeah.
minimum volume. Okay. Yeah.
Yes.
Great. Thanks.
So, right. Since it's in debug mode, it will take a while, so I'll just kill it. Right. Now, the next part of the presentation is how does it do the operations in a way that leads to minimal volume. Because if you just start randomly placing cubes and then connecting them, you end up with a monstrosity. It's like it's huge. I tried it. I mean, like it was just too huge if you did it randomly. So the first trick or like method that we use is something that's called beams. Out of each of the nodes come out beams indeed, and they come out from the faces to which you could attach a new edge. And those beams guarantee, one, that you know where the available exits are, and two, that you don't block them in the operations that you do. So they clear the path to and from the edge, the cubes that still need connections. Notice that not all of the cubes have beams. The beams only come out of cubes that still need connections. And they are used to avoid operations that would create problems. So for example, this comes from the GS set example that I just ran. In this case, it's creating a path from 3, which was already placed in a previous operation, to 2, which needs to be placed. And the pathfinder tells, well, actually, we could go up or down, or we could go right. So once the 3 results come back to the graph manager, the graph manager says, okay, yes, we could do that in a topologically correct way, but there will be a conflict because we need 3 exits for the next one. And if you put it up or down, you only end up with 2. And that is done by checking how many of the beams are broken by pre-existing structure. There's also another operation that is called critical beams, which ensures that we don't overdo these. So for example, if this number 2 only needed one more connection, then it will be fine to throw it up because there are still 2 green beams. So what the critical beams do is to signal a minimum number of beams that are needed for any operation. Now, it doesn't signal which. It just says, actually, we can break one of them or we can break none of them. So in this operation, you can see that this block, the one that is like a circle there, needs 2 operations. And because of that, the path went through the other side of the structure. If it only needed 1 operation, it might have gone to this side because that block has still 2 beams coming out of it. That helps 2 things. It helps to ensure that one operation I do now does not block me in an operation that I need to do 5 iterations down the line. And it also collaterally helps to lower the volume because that allows us to place very short length paths and to manage them aggressively. Since we know that they're actually not going to block future operations, then we can be aggressive in how we build them. Instead of going out, we can actually like keep it close to the center. And the other type of operations that are very important are symbolic computation operations that ensure the correctness. If we go all the way back to, and I'm actually going to do this just here, you'll notice that each cube has its own kind. Let's go over this one here, just in the leftmost side of the set. The set corresponds to the blue on this side and the backs on this other side. The X corresponds to the red and the red on this side. And the other set corresponds to up and down. So that is the way in which they're arranged, which means that the names are not only tied to the specifics of the surface code, they're also tied to the 3D coordinate space. And what that means is that the one at the beginning, it's always going to tell you which color this face is. The one in the middle is always going to tell you which color this face is. And the one at the end is always going to tell you which face this is. Once you have them tied to the coordinate system, they actually become symbolical in a pure mathematical sense, which means you can perform operations with them, not in the same way as if they were numbers, because if they were numbers, you would get a number out of a result, but you can apply the rules that you would apply to a numerical coordinate. So this is done to perform a number of operations that ensure that the blocks always align, that the block chosen for the next operation is always a topologically correct choice, meaning that the color continuity is preserved. And by preserving the color continuity, you are preserving the, let's go back to the correlation surface. You are preserving the structure needed to maintain the continuity of the underlying mathematical structure that will be like running through all those operations. The type of operations that you can do with these symbolical kinds are to ID exits, as I just said. Each, depending on where the letter is, it will like signal to you which color is goes in which direction. And there is a convention that says that the where you can place the exits is on where there are 4 colors. So the block is the color of the block corresponds to the faces that there are only 2. So if you have 2 blue faces, it will be a blue a set. And then to a set, you can attach edges on the red faces. So with that, we can identify the exits for any block. We can also identify the direction in which the edge runs by looking at the O marker and the position of the O marker. We can also do rotations, which are the coolest thing. When you have a Hadamard, what the Hadamard does is like to do a patch rotation, basically. Now, the Hadamards only have one name, but when you rotate the patch, you can also rotate the name because, again, the name is tied to the coordinate system and you can apply mathematical operations to it. So if you are rotating the patch, which is a 2D surface, you are rotating it mathematically. And if the name of that 2D surface is attached to the coordinates, you can rotate that with the same exact rotation metrics and get the rotated version of that name. So in order to tie it to the incoming one, we use the regular name. And after we do that, we know that the next one will need the rotated name. And this is achieved with like a symbolic rotation. It has many other subroutines that are very interesting. So the way in which it selects the central nodes. Here you have a graph which has 4 central nodes, except this one is actually more central. So it is a soft centrality measure. If there is one that is like completely like the center of the graph, it will go out a little bit to ensure that there's enough variety to build different versions of the structure. And it has the other reprocessing method that I just explained, which graphs that have more edges that could be processed in a 3D manner are broken apart. This is the example of how you break apart a single spider graph. But any graph which has, for example, one spider with 5 edges will get pre-processed too, in a way that the graph that undergoes the lattice surgery only has spiders with at most 4 connections. And well, that's sort of it. Let's see how I'm doing with time. Not bad. The idea with this is to try to entice you to contribute because there's so much to do. There's many gates that still need to be implemented. There are bugs that need to be fixed. Benchmark spending, so we want to do randomized testing to see how this performs with like many different kinds of circuits and many different sizes of circuits. There is a need for more algorithms. Some of the rationale that I used to design the initial algorithm is to like do something that will not fail, and because of that, I went with a Dijkstra path search, which is not particularly fast. So it would be good to like find ways to make it quicker. By that, I don't mean that it's too slow. I mean, each one of these things builds in like fractions of a second. But it could be even less, and that will be better. And there is ample space for contributing in other ways, better being management, additional symbolic operations, better ways to manipulate the incoming graph so that the volume of the final lattice surgery is lower, and many other things. So since we have time, I wanted to go and like run a few other examples to give you an idea of the variety of structures they can build. And we can start with a CNOT. This PySex one, well, that's the result, sorry. I'll put in different kind of visualization so it's easier to see the process. And let's run a CNOTs. The process is always the same. It identifies an initial node and it builds the structure node by node, following the CX graph and ensuring that the next operation is topologically correct by matching each block in the path, by matching the colors of each block in the path. And it can do this for surprisingly large circuits, actually. Let's just do one more.
Sorry, can I ask you a quick question?
Yeah, go for it.
In this 3D graph, the time is the vertical axis.
Yes and no. So the time is the vertical axis, but we have operations in the next tool in the pipeline that allows you to rotate the structure. So if you have if you have a result that you think, well, I don't want to run it in a way that the time corresponds to a set dimension, I would prefer if the x dimension would be time, you just take it and rotate the whole thing, put it up. So yes, with that caveat.
Okay,
And
so
it's
any
also important to go back to the whole thing of the surface code and the correlation surface, that the correlation surface is a mathematical object, right? So it doesn't necessarily believe in time, to put it like that. I mean, if you have the full correlation surface, like the math will add to what it needs to add, regardless of like the direction in which you're looking at it. So time, it's a really interesting construct with the surface code that I honestly do not understand that well. Uh, and that's why I build this using 3D objects rather than like the underlying mathematics of the surface code. Does that answer the question? If not, I can ask help from people who are also in the call that understand this particular aspect of time better than I do.
Oh no, yes, just because I think about lattice surgery as a sequence of operation. So you do first this, and then you do then that, and then that. So I was just trying to read that 3D graph as a sequence of operation. Mm.
So yes, no, I completely share this because it's very difficult to think of the final build surgery in a timeless manner. And in a way, because it is being built cube by cube, you do get the sense that you're like going at it in a way that is like incremental. But when you have the full result, and let's just put it here, this is a steam. When you have the full result, and you think about how the correlation surface would go, topology doesn't do the correlation surface, like the next tool in the chain does it. But let's just like say for a moment that you just go here and here. once you have the correlation surface, it really is just a mathematical object. So if you pull it from one side or pull it from the other one, it will be equivalent. So that's why with the full built lattice surgery, it doesn't really make so much sense to think of time. Although I myself always find myself thinking, yes, but does it? That said, if you do, if you have a chip that like kind of run it like this, maybe you can like just do it like that, and you can visualize it in a completely different way. With the next tool, you can actually rotate this in any direction that you want. Not sure if I answered your question, to be honest with you.
Yes, I think so. Thank you. So
Okay.
by rotating, you could also just say changes the time it takes for the circuit to run, right? Because maybe one side is very long, but from the other side maybe it's more large, but it takes less time. Is it a right intuition?
Yes, but you also need to remember that you have a chip with limited area. So this thing could not run like in this, this could not run upwards because it wouldn't fit in a regular chip. I would actually need a very, very long, big chip to fit because you have many parallel operations happening, especially here. But if you put it like this, then each layer would have less concurrent operations, and maybe these would fit. We're also working on a different way to do the beams so that the structure can flow upwards instead of like around a central point. But yes, depending on like how elongated it is, you would need more layers, computational layers to actually run through the full thing. So if you can fit a flat version of this in a chip and get it done, then this will be faster. But the problem is this one, for example, you wouldn't be able to fit because you need all these layers running concurrently.
Yes, thank you. Perfect. I understood it. Thank you.
Perfect. I don't know if more questions.
I have one quick question, probably the silliest one, but I was wondering, is there any focus on dynamic control flow in this project, or no? I'm asking, given you added Crisp as a supported front end.
So no, mostly not. Certainly not now. There is no focus on dynamic control. And in the future, that would be handled best with the next tool in the TQC pipeline. That said, there is something that we need to implement at some point because when we add more gates, there is a need for some gates decide a sequence of operations. So we'll need to somehow make a hierarchy of cubes when there is a need to wait for some parts of the structure to like be done. We'll need to add some kind of hierarchy there to manage that. But even that, we would only be giving the hierarchy. We will not be really giving like the operations needed to control that. The controls would like need to be handled completely on the next parts of the pipeline.
I see. Understood. Thank you.
Could you
Let me ask
post
you.
a
Oh, go. Sorry.
could you post a link for this? Sorry.
Yes, absolutely. Let me just find a way to. Oh, there we go. Now you can see my face. There is 17 messages in the chat. No idea. Quick question, is there not control flow? Okay. Yes, okay, we answered the question of making error correction codes smaller. Instead of thinking of them, making them smaller, I would think of them of building them with the least amount of operations needed. which by extension makes them smaller. But I don't really think of making things smaller. I just think of them, or I just think of the challenge of like getting through the whole graph as quickly as possible. And because it is a spatial, since it is a spatial algorithm, the speed depends on the amount of coordinates that you visit throughout your process. So the least amount of coordinates that you can visit, the faster you'll build it, and the lower the volume of the final result. Um, there will be a recording, yes. And I think,
Yeah, I think that's pretty much the question in the chat.
yeah,
I think you have already answered them during the talk.
yeah, okay. And the link is there. The last message is the link.
Mhm.
Yeah.
Are there more questions from the audience? If not, let's thank our speaker again. Thank you so much for giving the great talk, and we will post the recording in our GitHub repo, in the Quantum Wednesday repo. And yeah, thank you so much, and thank you to everyone for joining. Yeah.
Thank you very much, Ariel.
All right, have a good day. Bye.